well, welcome. And again, thank you for coming out in either 0 degree or 3 degree weather, depending on which thermometer you believe in. So my name is Chun Yu. I'm an astronomer here at the Denver Museum of Nature and Science, and I will want to welcome you on this very cold night. And what we do in 60 minutes is we talk about the latest space science news of the past month. So this is a monthly program. It's the last Wednesday of each month. So in March, we'll have the next one. And so definitely look forward to that. And I am an astronomer by training, so I study things outside of the solar system and beyond. And today we will be covering all things related to galaxies, of all things. But in future events, if I'm not here, we might have an external astronomer or planetary scientist, in which case you might see other topics. So definitely keep a lookout on announcements for future 60 minutes, and I'm going to get started. And if you, since this is a relatively small group, because I think most people did not want to come out tonight, if you, we're going to save the questions for the end, but if you have like a super burning question that you absolutely must get answered right at that very minute, feel free to shout it out, and I'll try to help out if I can. All right, so with that, I'm going to get started. And like I said, we're going to be talking about galaxies tonight, and galaxies are basically just gigantic conglomerations of stars. Our sun is in the Milky Way galaxy. And what I want to talk about first is how do galaxies evolve in the universe? Because most of you know that our universe began with the Big Bang. And what came out of the Big Bang was an extremely smooth collection of gases and atoms, and galaxies develop later on. And the way that we think galaxies evolved can be sort of summarized in this animation. And so this is a computer simulation. And what we're about to see is the evolution of galaxies. And galaxies basically evolve by merging with other galaxies. So here we're seeing what you can sort of think of as like a proto-Milky Way, a spiral galaxy. And And even though the universe is expanding, gravity is still in operation. And so what is happening is that gravity is pulling matter together at the same time that the universe is expanding, and space between galaxies is supposed to be getting larger. But again, gravity is pulling matter together. And as the mass falls into the galaxies, the gas turns into stars, and you'll even see dark material show up as well. Those are molecular clouds. Those are gigantic masses of molecular gas, which collapses to form stars. And you'll even see sort of outbursts as well, because when stars form, when they turn on, the more massive stars send out lots of stellar winds, they have UV radiation, and they have supernova, gigantic explosions from the most massive stars. And those tend to disrupt the galaxy, and they disrupt the gas clouds as well. And as this animation continues, you basically have a nice-looking spiral galaxy, and we might see one or two more things accrete onto it. But over time, I mean, what basically happens is the galaxy grows larger, and then the other important thing is that they become enriched in heavier elements. And I'll explain what I mean by that in just another minute. And what I want to do is just watch another animation. And we know that our Milky Way is actually surrounded by smaller satellite galaxies that are in orbit. So you might have heard about the Large and Small Magellanic Clouds. And this is a simulation showing basically a clone of the Milky Way that's merging with a much smaller galaxy. So the Large Magellanic Cloud is on the order of about 1% the mass of our Milky Way. And so you can see this merger, and during that merger, the gas collides with gas in our galaxy, It collapses, those gas clouds collapse to form new stars. And again, like I said, the stars can drive winds and supernova explosions. And so you basically get this somewhat chaotic environment where the galaxy itself gets disrupted by the actions of star formation. And then the other thing that star formation does is it builds heavier elements. So here is the periodic table of elements that everyone has seen from probably middle and high school science classes. And so these are actually all the elements that originate naturally in nature. And obviously there are a lot more heavy elements that we produce in nuclear reactors. But the two primary elements that are produced in the Big Bang are hydrogen and helium. And so most of the universe is made up of hydrogen, and about a quarter in number is helium. And there's a smidgen, you can see kind of a red band here, that corresponds to a tiny amount of lithium that's also produced in the Big Bang. But as you can see in all these other colors, that most of the elements are actually created from stars. And so either low mass stars like our sun, as they die, they expel, while they live, they create heavy elements. And when they die, they throw out their outer envelopes and disperse those heavier elements out into interstellar space. And they're also exploding massive stars. These are the supernova that I was talking about. Exploding white dwarfs. White dwarfs are they're basically end products of low mass stars. When they die, they end up their cores collapsing into white dwarfs. And those white dwarfs, if they happen to be in a binary system, they can end up colliding and exploding, or they can accrete gas from a binary companion, and that can lead to an explosion. And so you can see these blue elements here that are primarily created from exploding stars. And then there are these yellow elements that are predominantly yellow that are those elements are made from merging neutron stars. So neutron stars are the end lives, the end products of massive stars after they blow up in supernovae. And if you have, again, a pair of stars that are massive, they're orbiting each other, and if both of them end up being neutron stars, and if they end up colliding or merging, they will again have a big explosion, and that throws off and creates at the same time all these much heavier elements. So one of them, for instance, is Au, which is gold with a element number of 79. So if you have gold jewelry, you know that the vast majority of those gold atoms were created in neutron star collisions and explosions. So that's one way that we all are connected to stars. Now, one of the things that astronomers do is that because hydrogen and helium are so predominant in after the Big Bang, and they make up most of the matter in the universe, and all the rest of the periodic table only makes up a few percent, roughly. What they've done, astronomers have called all these other heavier elements, they just gave it a name of metals, which sounds really confusing because obviously not all these elements are metals, and I won't use that term metals, but that's something that you might hear if you hear astronomers talking. But what I just wanted to point out is that these heavy elements, because they come from stars, what happens is that if you have generations or multiple generations of stars forming, they will basically pollute the galaxy with heavy elements. So the longer you wait, or the longer you're looking at a galaxy as it evolves over the course of the lifetime of the universe, the more star formation takes place, and the more of these heavy elements slowly build up in a galaxy. Now, the other bit that I want to mention is that in our Milky Way, we also see a lot of globular clusters. In fact, we've observed about 150 of these, and these are basically small, compact gravitationally bound clusters of stars, and they can have anywhere from tens of thousands to millions of stars. And when you photograph them either from the ground, through a telescope, or if you get a chance, even looking through a telescope at some of the brighter globular clusters, you'll actually see a cluster that's very dense at the center, and then the density of stars drops off. But they typically have these nice round spherical-looking shapes. And one of the questions that still puzzle astronomers is where do globular clusters come from, and how did they evolve with our galaxy? And because what we find is that these globular clusters tend to have extremely old stars. And so they formed and started orbiting the galaxy at the very beginning of the evolution of our galaxy. And we see that not only in our Milky Way, but in other galaxies as well, where we can observe globular clusters. So the exact details of how, what the origins of globular clusters are is still somewhat puzzling, but we're going to talk a little bit more about, potentially solving this puzzle, or at least adding an additional piece to the puzzle with observations of the James Webb Space Telescope. And James Webb, unlike the Hubble Space Telescope, is primarily focused on infrared wavelengths. So it's basically detecting wavelengths of light that our eyes are not sensitive to. And you might remember this image, which was the first public image released from James Webb that was part of a big public announcement made at the White House last summer. And what we're seeing is basically a pinpoint in the sky. And James Webb observed this position in the sky for about 12 and a half hours. And so what we are effectively seeing are tens of thousands of galaxies that are along this line of sight that James Webb is observing. And because light travels at a finite speed, what we're seeing are basically not only nearby galaxies, but also more distant galaxies along this. You can sort of think of it as a pencil beam. But because light travels at a finite speed, the more distant galaxies, their light took longer to get to us. So we are effectively looking at things back in time. So the nearby galaxies have light that's emitted more recently in the past, and the very faint smudges in this picture are much more distant galaxies, and their light was emitted much further in the past. And so, in effect, what we're seeing is a bunch of not only nearby galaxies, but galaxies that are relatively recent or close to us in age, and much more distant galaxies that are much older. So we are seeing those galaxies in the past, perhaps hundreds of millions of years or billions of years. Now, the other aspect of this picture, clicked on the wrong button, is there are lots of weird-looking arcs. You might notice that seem to circle the center of this image. So you notice these stretched out lines, and those are actually distorted images of galaxies that are much, much further away. And so what is happening is that there's a foreground cluster of galaxies, probably hundreds, if not thousands of galaxies, and the gravity of all these galaxies is enough to bend or refract light that's traveling to us. And so you can even think of this as like a gigantic lens. And in fact, astronomers call these things gravitational lenses because they use gravity to bend the light. And just like you can use a lens to look at things magnified, what we're seeing are basically magnified images of galaxies that are much, much further away. And they've been magnified by the matter that's contained in this foreground cluster. And some of these background galaxies have been magnified by hundreds of times. So in the same way that you can use a telescope or a microscope to magnify and zoom into objects that are either further away or things that are too small to see, this is exactly what is happening in this image. So we're seeing galaxies that have been magnified. And if we zoom into this particular box, and we're going to look at this box. So here is that box again. These are actually foreground stars, and so we can ignore them because they're located within our galaxy. But there are three different objects here that are numbered 1, 2, and 3. And this is something that I actually talked about last year in a previous 60 Minutes in Space. But these happen to be the same galaxy that, because of the lensing effect, look distorted. And they've also been, the image has been multiplied. And this is, again, just due to this gravitational lens. And so, in effect, even though these look very different, and again, this is a foreground star, so you have to look at this thing over here, but this, and this are three different images of the same background galaxy. And you'll notice all these little bumps or dots that surround the galaxy. And because of these dots, people started calling this the sparkler galaxy, because they think of these as being sparkles or glitter. And so this galaxy, the light emitted that we're seeing left about 9 billion years ago. And this galaxy is about 1 billion solar masses. And so it's about 1% the size of our Milky Way. But this is a very, very early galaxy. And what astronomers interpret these dots to be is that some of them turn out to be globular clusters. So they are, right now, the oldest globular clusters that have ever been detected. And so it's about 5 to 6, depending on the scientists you read, or at least their papers. A couple of these sparkles turn out to be star-forming regions. And so the regions where many hundreds, if not thousands, of stars are being formed. Whereas if these globular clusters might be a lot older, and in fact, they turn out, as we'll see, they do turn out to be a lot older. Now, one other bit that we'll need to understand this galaxy is this plot. And this is a little bit complicated, so I'm going to try and explain it. But this is basically a theoretical simulation showing how galaxies evolve. And so this is time in billions of years. So the present is over here on the left, 0 years ago. And then we're basically going back in billions of years. So the Big Bang started 13.7 billion years ago, so just shy of 14. And these lines represent the different evolution, the evolution of different galaxies. And so the bigger, more massive galaxies are the lines off to the top and to the right, and the less massive galaxies are these darker lines that are at the bottom. And along the side is a plot showing the amount of heavy elements that are in these galaxies. And so what we're seeing is that if you let's follow this yellow line, which is the most massive galaxy. So you can imagine this galaxy forming early in the Big Bang. And just like that animation we saw at the beginning, what happens is these galaxies will basically grow over time because gas will be attracted towards the galaxy gravitationally, and that gas will pile onto the galaxy, and those gas clouds that form will form stars. And so what happens is that initially there might not be very many heavy elements because star formation has just gotten started. But if you follow the galaxy evolution over time, what happens is more and more gas piles on. And so you expect the galaxy to start moving in this direction as it moves towards the present. But as star formation continues, more and more of those heavy elements build up. And so that's why this galaxy starts moving up. So from perhaps less than 1% to 3.5% to 10%. This is a logarithmic plot. And so until you get all the way to the present, in which case you have a galaxy with heavy elements that are comparable to what we find in our sun today, or in our Milky Way today. And similarly, if you follow the least massive galaxy, you get pretty much the same sort of curve. It's growing over time, and it's having lots of star formation. And as the star formation pollutes the galaxy with heavy elements, you see the amount of heavy elements grow from less than 1% to about 1/3 of the heavy elements that we find in our solar system or in our sun today. But what's interesting is that if you look at these curves, they don't, for the most part, don't cross, and they all basically move, they more or less increasing at all times. And so what that means is that for the larger galaxies, you can basically distinguish larger galaxies by how much they have in heavy elements and by their age. And so if you find a galaxy that's somewhere over here, as opposed to a galaxy over here, then you know, you have a good sense of how big it is and how big it'll end up by the time you get to the present. And so astronomers were able to basically use a similar analysis for those sparkles, for the sparkler galaxy. So this is a very similar plot, but we're plotting from 6 to 14 billion years ago. We're not going all the way to the present. And again, we're looking at the amount of heavy elements in the galaxy. And so the globular clusters that are associated with the sparkler are plotted over here. And then it turns out that there are two clusters that are showing more recent star formation. So they're not globular clusters, but they're just more recent star formation that's occurring. And then there's also this pair of somewhat anomalous clusters, and in this particular paper by Forbes and Romanovsky, they interpret this to be a satellite galaxy that's merging with the sparkler galaxy. So basically, the interpretation of this is that these globular clusters formed early on, or in the history of the universe and in the history of that galaxy, but there was so much star formation that these globular clusters ended up having lots and lots of heavy elements. Whereas this particular satellite galaxy that's merging with the sparkler, it didn't have as much star formation, and so it has much fewer heavy elements. So it's way down here, as opposed to these globulars, which are up here between 10 and 50% in heavy elements. Now, what's also plotted, the stars or globular clusters in our Milky Way. So you notice in our Milky Way, we have globular clusters that are also have similar amounts of heavy elements as the globulars in the sparkler. But we also have globular clusters that don't have as many heavy elements. So the stars, stellar star symbols that are further down in this image. And then also plotted is the Large Magellanic Cloud clusters. They're actually not globulars, but they're just star clusters in the Large Magellanic Cloud. And so you can see the satellite galaxy, which is in orbit around our own Milky Way, it tends to have, it doesn't have as much heavy elements, so that means there's been less star formation that's taking place, which again makes sense because the Large Magellanic Cloud is a much smaller galaxy, and so you don't expect as much gas falling onto it. You don't expect as much star formation, right? So here is the sparkler globular clusters, and what we're plotting here is these symbols represent different theoretical tracks. So these are simulations of galaxies of different masses or starting masses, and so you see that the green triangles represent smaller galaxies between 1 and 3 billion solar masses, the blue triangles between 3 and 10 billion solar masses, and then the purple representing galaxies that are starting off with between 10 and 30 billion solar masses. And so this sort of follows the plots that we had seen previously, where the more massive galaxies follow the top line, and the less massive galaxies follow the bottom line. And again, it seems like for the sparkler, those globulars seem to have formed very early on, and they had such an intense burst of star formation that, and probably multiple rounds of star formation, that they ended up with a lot more heavy elements than you would expect, because normally for a smaller galaxy along these curves, you might expect the heavy elements to be down here. So basically, what this is telling us is that this is the first of hopefully many clues in the future as we observe more globular clusters to more and more distant galaxies, and we're seeing those distant galaxies further in the past. We'll basically have a better idea of how globular clusters got to where they are in orbiting parent galaxies, and how they ended up having so much heavy elements via the star formation process. All right, so that's the end of my first story, and what I want to do now is go on to the next story. It's actually one big story, but there are multiple parts. And again, this has to do with galaxies, and this is a project called Physics at High Angular Resolution in Nearby Galaxies. And astronomers love to have acronyms, and so if you cherry pick specific letters in that phrase, you'll see that you have this cool sounding name of FANGS. And the idea behind FANGS, and this is a program that over 100 astronomers have been involved with for the past decade or more. And basically, their intent is to try and study face-on spiral galaxies. So here's one example of that. And by face-on, spiral galaxies are basically sort of shaped like dinner plates or pizzas, meaning they tend to be relatively flat as far as most of where their stars and the gas mass is. But so if you are looking at that dinner plate or pizza at John, you can't see a lot of detail. And there's stars and gas that are hidden by the foreground material. But if you, instead of looking at it at John, you look at it face on, now you can see all of the detail in the core of the galaxy and in the spiral arms. And in the spiral arms, you notice that there's lots of gas. That's the dark material, as well as stars that also follow the spiral arms. You can even see that the bluish stars tend to follow the spiral arms. And those blue stars basically mark the locations of star-forming regions. The blue stars are more massive, and they're much brighter. And so when stars form, you tend to find only a few bright blue stars, but they tend to outshine all the dimmer, brighter stars, and then they blow up in supernova. And so there's no time for the blue stars to migrate away from the spiral arms where they're born, whereas the longer-lived, lower mass, or redder stars, they tend to be sort of equally spread out throughout the disk of the galaxy, because they, like our sun, can live for many billions of years, and so as they orbit the galaxy, they just slowly migrate away. And so FANGS is looking at face-on spirals so that you can actually study all this structure. And they also are looking at relatively close by galaxies, or on average, perhaps only 50 million light years. And what that does is it helps us find galaxies where using modern telescopes, you can see lots of detail in the structure of these spiral galaxies. And so the big goal is really understanding not only star formation, but how the structure of these galaxies change and evolve because of the star formation that's taking place. And then finally, FANGS involves multiple observatories, both on the ground as well as in space. So this is a Hubble Space Telescope image, but from what I understand, a lot of the work that got FANGS started was actually done on the ground. So the ALMA radio observatory in Chile, which is a bunch of radio dishes that are connected together that effectively form a much larger telescope, they're able to, using radio observations, basically get information about the cold gas in these galaxies. And so you can see that the cold gas, which can be just tens to up to maybe 100 degrees above absolute zero, they also tend to collect in the spiral arms. And so this gas is the precursor to stars. As the gas forms and collects, what happens is instabilities cause parts of the gas cloud to collapse, and those gas clouds can then gravitationally collapse to form many hundreds, if not thousands, of stars. Now, just in the past week, there were 17 papers that were published simultaneously from this project. And like I said, FANGS has been going on for quite a few years, but what they were publishing on was new results from the James Webb Space Telescope. And so just to give you an idea of what James Webb does, as opposed to, let's say, the Hubble Space Telescope, let's look at a few example galaxies. So here is one of the galaxies from the FANGS project called NGC 1365. And what you'll notice is that here's the bright center of the galaxy. And this glow that we're seeing is from many tens of billions of stars. So the stars are so far away, and they're dim enough that we don't see an individual star necessarily, but we see the collective glow from all these stars all together. And so this yellowish glow is from those older, less massive stars that we were talking about. We also see lots of molecular gas. So this is the gas clouds that eventually collapse to form stars. And you also see, like I said earlier, the brighter bluish stars. And you can see there are multiple clusters of blue stars. And the blue stars, again, show up because they're far, far brighter than the low mass, the less massive stars, which are yellowish. And you also see that these clusters, these young clusters, tend to congregate near the spiral arms. And again, that's a hint to how they formed, because these stars basically form from the collapsing clouds. So now that we looked at this with the Hubble Space Telescope, we're going to see what it looks like with James Webb. So here is the same galaxy. You can get a hint of the same arms structure, but because James Webb observes in what we call the near-infrared and the mid-infrared, infrared light can pass through gas clouds much more easily than visible light. And so whereas here you kind of get a hint of where the gas clouds are, and you get a hint of the spiral arms before the arms kind of peter out, in the infrared image you really see the spiral arms. And so the light that we're seeing here is actually glow. You can sort of think of it as the glow from the heat of these gas clouds that make up the spiral arms. And peppered along the arms are these reddish regions. So you can see, they're almost like measles. And these are those young stellar clusters that I've been talking about. And depending on the wavelengths of the light, you can pick these clusters out. And so you can see we can really distinguish the arms that are highlighted by the cool molecular gas, as well as the regions where star formation has taken place, where you have these bright young clusters showing up. And in the infrared, you don't really see the individual stars. So if you look, let's go back. You can see that there are lots of bright young stars that are kind of spread out in these clusters, but those individual stars don't show up. You really only see the most concentrated parts of those star clusters. All right, let's look at another galaxy. Here's NGC 1433. This again is another image from the Hubble Space Telescope. So we're again looking at light that's visible through our eyes. And we see the spiral arms highlighted by the molecular clouds. We see the bright whitish blue of star-forming regions. And you can see that the young clusters tend to be a little bit further out. And then there's also kind of this interesting kind of oval structure towards the center where gas is orbiting the center of the galaxy. And then here is The same galaxy from James Webb. So again, you see the spiral arms really showing up. And again, we see the young stellar clusters showing up in these reddish dots. And you'll also notice that the gas tends to be sort of stretched out along these arms, but you also get a sense that there's kind of compartmentalization going on, that there are the gases forming around what could be cavity. You can think of as cavities or voids or bubbles. You get a sense of that. There's like a big bubble here, and just from this picture, and there's also kind of a longish oval over off to the right, as well as one over here. My laser pointer is dying, so it's hard to point stuff out. But you can see lots of cavities, and what we think of, the way that astronomers interpret this, is that as stars evolve and they explode or they expel stellar winds, those winds and those explosions push out against the gas clouds. And so that's why you have these bubbles that look like they're devoid of gas, but surrounding these bubbles are walls of gas. And so these walls of gas are basically caused by the stars that are formed from the gas clouds. All right, here is NGC 7496, another example of this. I don't have to go through all the different parts because you're probably experts at identifying the different parts of the galaxy. So let's look at it again from JWST. And we see that same sort of structure where it looks like there are these voids that have opened up in the gas clouds. And those, again, are due to actions from the stars themselves. There's lots of star formation going on. You can see how heated the gas clouds are up here in this particular arm. And there seems to be like a giant bubble that is formed, and there are a bunch of star-forming clusters at the edges of this particular bubble. And if we compare, and actually I'm not even sure if I quite have it lined up, but you can see that there's not quite any obvious structure in the visible image. All right, here is an image that I actually showed last month for people who were here in January, and this is a galaxy called NGC 628 or Messier 74. It also has this curious name of the Phantom Galaxy, and the reason why they call it the Phantom Galaxy is that out of all the Messier objects, this is the hardest one to observe because it's the surface brightness of this galaxy is so faint, so it's difficult to see with a small telescope that amateur astronomers might use. And so this Phantom Galaxy has, at least the name is stuck in press releases. And when we look at this with James Webb, here is, again, that very weird looking skeletal like structure showing all the molecular clouds. And again, with all these big voids. And what the paper that I'm going to talk about, they kind of focused on this really big void that's over 3,000 light years across in the Phantom Galaxy, and they call it the Phantom Void, to continue that naming scheme. And the paper, one of the 17 papers that were released all simultaneously, has 54 authors. So, this is a lot of work involving not just James Webb data, but data from lots of different telescopes. That's why you end up having so many astronomers involved. And here is one of the figures from the paper. So the image of the galaxy has been turned around by 90 degrees. So here's the phantom void. And here is a zoom in to that. And so this is, again, about 3,000 light years across. And they even find something that they call the precursor phantom void. And so they think that this precursor is an earlier version of the phantom void. And you might notice that these aren't the only voids. I mean, there's lots and lots of bubbles everywhere. And the locations of these bubbles is actually from another paper that was part of that big release. And so in this other paper, the astronomers on this paper, the authors, went in and manually identified over close to 1,700 voids that are in this galaxy. So here you can see all of the bubbles and voids that they identified, and those are basically plotted in that previous image, which we're zoomed into even more now. And so what you'll notice is that, well, again, this is the big void. This precursor void is only about 160, 170 light years across. But what we see is that the void tends to be empty of gas clouds. So the infrared shows the warm glow from the gas clouds. And so the clouds don't appear in the center of the voids, but they do appear in what we can sort of imagine to be a shell around these voids. And you can also get a sense that there is like a shell-like structure. It's not uniformly the same thickness or density, but there is a hint of a shell in the precursor void, and then you also kind of get a hint of shells in some of those other voids as well. And so as part of their effort, not only did they look with James Webb, but they also observed with a lot of other telescopes. And so here, in these diagrams, they even highlight what the difference between the so-called bubble versus the shell. And so again, the smaller, thinner oval is the bubble, and the bigger circle represents the void or the shell surrounding the void. This is the main phantom void, and this is the smaller precursor phantom void. And this is the James Webb image, the blue image on the left. And so, like I said before, we're seeing gas that's been warmed up, or relatively cool gas. And so there's not that much gas inside the bubble, but most of the gas is piled up in the shell. The middle image in red is from the Hubble Space Telescope. And this image basically showcases light from an emission line of hydrogen. And this is light that's emitted by hydrogen after it's been irradiated by ultraviolet radiation from massive stars. And so again, that gas that's being ionized tends to be in the shell. You see very little emission in the centers of the bubbles, but there's also lots of emission in that precursor. And then finally, if you look in the ultraviolet or the near ultraviolet, that's what NUV is, in this right diagram, that shows you where the young star clusters are. And so you can see that there's, again, lots of star formation that has gone on in the shell, and there isn't as much active star formation or young stars in the center of these bubbles. And again, a lot of these brighter regions are associated with the young stars. And so what astronomers are basically interpreting from all this is that there have probably been multiple generations of star formation that have taken place, which is why you see lots of clusters of young stars. And as the most massive stars blow up and they die off, you are left with older star clusters. And so that's what this color bar up here represents. So the whiter colors for these star clusters represent the youngest star clusters. The bluer ones represent older ones. So you can see that there tends to be older star clusters in the center of the void, but to find the youngest star clusters, you have to look in the shell surrounding the void. And then you also see that the youngest, most massive stars tend to be right at the edges of these bubbles. And here is the remaining observations from this paper. And so again, they're using lots of different observatories, both in space and from the ground. But the main point that I want to point out just from this image is that this is the Hubble visible light image. And so, again, just to show you why we need to have not just James Webb, but other observatories, when you're looking just in visible light, the light that our eyes are sensitive to, you don't really see much of a hint of what is going on. So the bubble isn't really clear, and you do see a lot of these bright young stars, but again, without understanding where the void is or where the shell is, it's not clear how to make sense the locations of these young massive stars. So basically, the main takeaway from this work is that if you look at how many supernovas are required to blow up these bubbles, it only takes but one supernova to create the precursor phantom void, whereas to have a void this big for the main phantom void, it requires about 100 supernova. And then the other main takeaway is that we seem to find young stars forming at the edges of the voids, and older stars are in the center or in the middle of these voids. And so what could be happening, I mean, there's actually multiple interpretations of this, but one is that as the supernova explode, they are pushing the gas outwards. And so they're causing the gas either that's already existing in the void to expand outwards and collide with existing gas. And it could be that the supernova is causing further star formation. So as the gas clouds collide, they can collapse to form new stars. And so that's why you're seeing new star formation taking place at the edges of this void. Another idea might be that there's something called sequential star formation. So when the void is small, you might have stars forming at the center, but then because the stars, winds from the stars as well as supernovae can compress the clouds, what happens over time is that you get subsequent waves of star formation that start out in larger and larger circles, or the edges of larger and larger voids. So that's another interpretation. And so basically, these observations confirm what a lot of astronomers have long suspected, that feedback from stars are an important ingredient in understanding how galaxies evolve and how they grow. So not only is gas falling in, but the shapes of galaxies themselves, or the shapes of the molecular clouds, you can sort of think of them as being the skeletons or the bones of galaxies, just because they do look, strangely bone-like. They are affected by the star formation process, and new stars can form, but they also can blow out voids, and they can also cause subsequent waves of star formation to occur. So this is a very complicated process, but it's pretty fun and neat to see that all these observations are helping us kind of coalesce to some fundamental ideas about how galaxies evolve. And so with that, I'm done with my two main big stories, and I'm happy to answer questions from everyone. And I think we can probably turn up the lights too, Ollie. If anyone has a question, you might want to just shout it out since the lights aren't on. Yeah. Over here. Okay. Mm-hmm. Yeah, so you're asking about the idea that most of the mass in the universe is actually not visible matter that we can observe with telescopes. That there's so-called dark matter. There's also something called dark energy, which I'll skip for now, but it appears that dark matter is anywhere from 5 to 6 times more there's more dark matter than there is ordinary matter. So, ordinary matter is made up of atoms that we're familiar with, made up of electrons and neutrons and protons. But right now, dark matter is still very mysterious. People have a lot of ideas about what dark matter might be, but we don't really have any solid clues. And you suggested that, or you said that there are people who've suggested that black holes is a possibility. And I haven't studied enough recently about the recent work about that, but black holes are probably just one of lots of different ideas about what dark matter is. And in fact, if we go back to, let's see if we can go back all the way to the beginning, to the animations that we're watching. Try this again. These simulations, these computer simulations of how galaxies evolve, they actually require dark matter, because if you leave out dark matter, there's actually not enough matter to gravitationally pull mass together to form galaxies, and to form galaxies that are the sizes that we see today since the Big Bang. So you actually require dark matter to create the structure that we see in the modern universe. So astronomers have basically accepted that dark matter must exist in some form, because you can't get to modern galaxies without dark matter, but it's still quite a mystery as to what dark matter is. Yeah, all right, yeah. Thank you.
Is the space between the Earth and the Moon and Earth and the Sun, is that dark matter too?
So, one idea about dark matter is that it's a subatomic particle that hasn't been discovered yet, and dark matter, we think, so we're seeing stars and gas orbiting the center of the spiral galaxy in this animation. And the distribution of dark matter, we think, they're not clustered in a plane or in the disk like we see the visible matter. They orbit in what we call halo orbits, meaning they tend to orbit in every single direction. So they're scattered. They're more or less in kind of a spherical shell or spherical collection of dark matter around each galaxy. Sort of the same way that when we look at globular clusters, the stars tend to be clustered spherically. So if the dark matter does consist of subatomic particles, you would expect those particles, as they're orbiting the center of our galaxy, to be flying through our solar system, or flying through our bodies, for that matter. And so there are experiments that have been set up to try and detect potential dark matter particles, and if you can detect them, you can try and nail down what type of particle they are. But so far, we haven't been successful in detecting any new particles that could be a dark matter particle. But wonderful question. All right, any other questions?
There's a film playing at the planetarium called Dark Universe. What are your thoughts on that film?
Okay. Well, it's a film from the American Museum of Natural History, so they're the ones who produced it, the Dark Universe planetarium film. It's narrated by Neil deGrasse Tyson, so if you're a fan of Neil, you can go see it because of that. The film is a little old. It came out back in 2012, but it does cover a lot of our current ideas about the universe. So the reason why it's called Dark Universe is it talks about dark matter, it talks about dark energy, it talks about the modern ideas in cosmology. So if you wanted to learn all that in less than half an hour, and while watching some pretty amazing visuals in the planetarium, I encourage you to go see it. It's not a bad film. I was also an advisor for it, so you see my name in the end credits. But don't see it because of that. But yeah, if you're interested in cosmology and want to see a planetarium film about it, I encourage you to go see Dark Universe. Okay, there's a question here.
I was just wondering what year or era astronomy started being revered as a science.
What do you mean by revered?
You could talk to someone and they could say that science is established.
Okay. Well, I mean, astronomers, you can trace modern astronomy to the time of Galileo, who was the first person to really point a telescope to observe objects in the heavens. And so people have, following him, have used telescopes. But I think the explosion in scientific astronomy, in the sense of being able to really understand what stars were made up of, or what things that we're looking at were made up of, didn't really begin until the 19th century, when you had photography. And so you weren't limited to observing with your naked eye. You can use photographic plates to basically do long exposures and to collect a lot more information than you could just by observing with your eye looking through a telescope. So it was probably in the 19th century that you started seeing journals, publications that were more specifically meant for astronomers. Before that, there were more general journals where anyone interested in natural philosophy, which is what all of the sciences were kind of lumped under, you could submit a paper to. But as the sciences kind of evolved away from each other, you started seeing journals that were focused only on astronomy, or only on physics, or only on biology. But even then, astronomy was known only to the scientists. I mean, I don't think people, the public, necessarily knew about it unless they were using it, people were interested in knowing when the phases of the moon were happening, but for the most part, you didn't, unless you used it for your calendar, you didn't necessarily need astronomy. But in the 20th century was when astronomy really started to take off, because that was when millionaires started to fund telescopes and to fund observatories. And then after World War II, you started to have government funding. And so, in a sense, perhaps that's when astronomy really became respectable, because it attracted donors and government funding to, and you can sort of trace, the funding of a big, billion-dollar project like the James Webb Space Telescope today to those early funding efforts in the 20th century. So I'm not sure if I really answered your question, but that sort of gives you an idea of the history of astronomy, as well as how people have acknowledged it by giving astronomers money. Yes, sir. No, I'm definitely not rich, but interesting enough. I mean, if you think about, why does the government fund science? One reason is that science is you're funding it for knowledge's sake. Science is about discovering new knowledge, and so there is something intrinsically valuable to discovering new knowledge. There's a second argument that you fund science because it produces results that are useful for a society. And so the question is, how is astronomy useful for society? It produces lots of pretty pictures, which interests a lot of people, but oftentimes it's not entirely clear, but there are a lot of technological developments in astronomy that perhaps the astronomers don't necessarily invent themselves, but because they use these technologies, it's a way for these technologies to disperse out into the general public. So for instance, the detectors that astronomers use in their telescopes, whether it's infrared detectors or visible light detectors, a lot of that technology actually got started with military funding, because the military needed to have detectors that could detect individual photons, but those devices were relatively expensive because they were these used in sort of one-off types of applications. But after the technologies were invented, astronomers realized that they could be really useful for to put behind telescopes, and so they funded continuing development of those until you have detectors that were used in pretty much all modern-day telescopes starting in the 1980s. So a lot of the technologies were invented in the 70s, and then in the 80s and 90s they became ubiquitous in professional astronomical observatories, and then those same technologies slowly started showing up in digital cameras. And so the cameras that you have on your phones, in digital cameras, in standalone cameras, those all originate, you can find their lineage in astronomical detectors, which evolved from detectors that had military applications. So I suspect that's a lot of where the arguments are being made in different levels of government. Why should you continue funding astronomy at the levels that you do today is because it's a great way to get technological improvements and new technologies out to the public. Uh-huh.
So going back to what we were talking about, formation of galaxies, and we spoke of the pancake, or the inner plate of galaxies shaped like a really big frisbee. How does that happen? How do objects that populate a galaxy assume positions in the same plane of the ecliptic as opposed to a galaxy just being like a basketball?
Yeah, so that's a really good question. Why do spiral galaxies end up being shaped like pancakes and not like the globular clusters that we saw? Because we know that you can have globular clusters, which used to be small satellite. They used to be smaller galaxies until they were gravitationally captured. So how do you end up via this collision process to create the pancake? And it basically has to do with the gas. So if you have gas that's fallen in towards a galaxy, that gas tends to pile up in a disk as opposed to being in a sphere. And that's just because from the net angular momentum, angular momentum is basically a description of how something is in orbit or how it's rotating around a common center. And so, obviously the gas has fallen in from multiple different directions, but if you added up all the angular momentum, for it to pile up and be orbiting in perfectly circular orbits, in a spherical collection, the angular momentum has to be basically close to zero. But it's very unlikely for that angular momentum to be exactly zero for it to be orbiting in basically these halo orbits. But because there's a slight net angular momentum, what happens is everything tends to pile up and it all tends to basically orbit in the same direction. And so when you have gas colliding with gas, the net effect is you end up with that disk shape. When the gas forms into stars, or when you have galaxies that are mostly stars and very little gas, what happens is the stars, there's so much space in between stars that in these collisions, the stars will almost never actually collide with each other because the stars are so small relative to the distances between them that you won't have like a one-on-one collision between pairs of stars. And so the stars tend to pass right through each other, and their gravitational interaction will tend to result in those stars to form these halo orbits where they have kind of a spherical distribution. And so the reasons why you have elliptical galaxies or galaxies that don't look like disks is because those galaxies are formed from mergers where there wasn't that much gas, where the mergers tended to take place with smaller satellite galaxies that were mostly stars. And so those stars ended up being thrown out into these wider orbits. And for disk galaxies, spiral galaxies, you had mergers that were mostly gas, not as many stars. And so all the subsequent star formation that took place, those stars originated from the gas that's already in the disk. And so the stars themselves end up orbiting in the disk. So you basically have these kind of divergent paths in which galaxies can form. And the disk galaxies are the ones where mostly gas fell into those galaxies. But that's a great question. Do we have one more question? Yeah. Maybe the woman, since she hadn't asked a question yet.
When you talk about the heavy metals in the planets, how do you determine what metals are in these planets that are so far away? And how did our planet have finite metals if there's still pollution in the atmosphere?
Okay. Yeah, I think I was probably a little confusing in my discussion of the heavier elements, what we call the metals. And so going back to the periodic table and how, most, the Big Bang basically gave us all the hydrogen, helium in the universe, and all the heavier elements were produced in stars. And so that means that, if you think about planet Earth today, most of the elements that make up Earth, there's actually not that much hydrogen and helium. There's very little free hydrogen and free helium on Earth. It's mostly made up of heavy elements like carbon and nitrogen, silicon, all the metal elements that we think of, iron, nickel, copper, so forth. And so all those elements had to have been produced in stars, because you can see, if you're familiar with the periodic table and recognize which elements go with which symbols or abbreviations, you see that most everything had to have been produced in stars. So the earliest stars didn't have any planets, because there was or no rocky planets, because our rocky planets today have a lot of these heavier elements in them. So life, as we know it, couldn't have existed in the first few generations of star formation in the universe, because there weren't the heavier elements. Carbon, nitrogen, oxygen, those are all in the second row there. And those had to have been produced in either in the interiors of stars or in the process of stars blowing up. And so when stars blow up at the ends of their lives, when they throw out their outer envelopes, the heavier elements are still just a very minor fraction, just 1 or 2% of the makeup of the stars. But what happens is, because the stars, they blow up or they expand, they basically throw off the heavier elements that have accumulated within them during their lifetimes. And so as you look at a galaxy, starting at time zero, or after the galaxy was formed, and as you watch it evolve over hundreds of millions and then eventually billions of years, what you'll see is that the gas that's in that galaxy slowly accumulates heavier elements. And so at first it's just less than 1% of what we find in our modern day solar system. But just like these plots that we were seeing, that I was showing. So what's happening is that the galaxy, but the galaxy starts off down here, where you have less than 1% of heavy elements, and then over time the galaxy, these galaxies evolve on these tracks. So you're basically going forwards in time. You're starting off at the beginning of the universe here, and you're moving closer and closer to the present as you're moving from right to left, and then you're also moving up. And as you move up, the amount of heavy elements increases until you get to close to 100% in the present day. And the reason why it's increasing as you're going closer towards the present is because star formation is continuing over time, and each round of star formation ends up distributing more and more heavier elements into the interstellar medium, and those elements get collected in the next generation of gas clouds. Those clouds collapse to form new stars, and then so those new stars have slightly more heavy elements than the previous generation of stars, and when they blow up, when they die, they release those elements plus new ones that they created during their lives. So basically, star formation increases heavy elements in subsequent generations of stars. And so, so you would expect that as galaxies age, you would expect that 1 billion years from now, most of the stars that are forming in our galaxy would have even more heavier elements than they do today, than we would find in our solar system. So basically, heavy elements is just there's just one direction. They will continuously increase, and right now they're just a few percent. But as galaxies age, you'll find their percentage of elements or of atoms that are heavy elements will increase from a few percent to 5% to 10% and so forth. Okay, maybe one last question since we're running kind of pretty late.
I was just wondering, what was astronomy called before the 19th century?
Yeah, actually, I'm not aware of what any alternate names for astronomy, because I would. No, I mean astrology is something very different, because astrology is using, knowing that planets orbit in a very regular pattern and thinking that that has an influence on people on Earth. And if you think about it, you need to have some understanding of astronomy. You need to be able to observe the heavens. You need to be able to make observations and records of how planets and the moon, how they seem to move around the Earth before you can try to come up with astrology. So yeah, I'm not sure when the term astronomy came into being. I would have to look that up. But this whole idea of astrology. Have you ever wondered, why the Farmer's Almanac has, weather predictions? In the same vein that they, show you charts of the moon. It actually comes from this medieval idea that, it's older than medieval, but the astrology started with the Babylonians 4 or 5 or many thousands of years ago, but there's also this idea in the medieval times that weather could also be predicted because of using astrology, so that the motions of the planets could, if you understood that, you could also understand predictions you can make predictions of the weather. And the reason why we call meteors, it has the same name as origin as meteorology, which is weather, is because meteors were thought to originate in our atmosphere the same way that meteorology is associated with weather prediction, dealing with phenomena in our atmosphere. So there are all these connections between what was happening in the heavens with what was happening in our atmosphere to what was happening to people here on Earth. And so these are all related, and hence almanacs had prediction tables for planets and the moons, as well as predictions of what the weather would be like the following year. All right, so with that, we've gone off in some really weird directions in the Q&A, but I want to thank everyone for coming. And then I have one last slide, which I should have shown earlier, which is just the next date for 60 Minutes, which is March 29th. So I hope to see you at the next one. Thanks, everyone. And thank you, Megan, for holding the mic and running it around.